11:45. Okay. So in chapter 9, we had 9.1, in which we introduced the idea of approximating approximating functions with a polynomial. And this went back to the idea of a linear approximation being what you get when you use the tangent line produced by the first derivative. And then we extended that to the idea of higher order, nth order polynomial approximators of functions at some point of tangency, like a quadratic or a third degree or a fourth degree. And that basically there was a formula for doing that, which we will introduce later. And we call these Taylor polynomials. So this led to Taylor polynomials of nth order, which meant you just had third degree, fourth degree, fifth degree polynomials. But the way you got the coefficients of those polynomials was by using the first, second, and third order derivatives, and a little formula with a factorial in it, which we'll remind ourselves of shortly. So then in 9.2, we stepped away from the idea of a polynomial approximator of a function, and instead we focused on power series in general. What is a power series? It's an infinite order polynomial or infinite degree polynomial. So and we call this properties of power series. So power series were just like regular infinite series, going off to infinity, but instead we had C sub k as not just a constant, but a coefficient of x raised to the k power. So, and we started these with an index of 0 because you have a 0th degree term of a polynomial, which is the constant. Then you have first degree, second degree, third degree, etc. So this basically, the idea of a power series was this is just an infinite degree polynomial. And so when you have these things, we have to think about series like we had before, but now with variables in them. And then now the difference that we have to consider is that every time you plug in a different value for x, you get a different series that may or may not converge. And this led to the idea of a radius of convergence. And so there was a theorem about that, but we'll sort of go through these as we look at examples. Theorem 9.3, I guess I'll add that here. So in this section was theorem 9.3, which just talked about the fact that power series have a radius of convergence. Basically, there's some R value, and as long as you stay within that R value distance away from the center or the A value of a polynomial of a power series, that you get convergence. And when you exceed that R value, then you get divergence. And maybe R could be infinity so that you can't exceed it, and it may be that R is 0 so that as soon as you leave a 0 value, you get, as soon as you leave the center value A, you get divergence. But that it's equidistant in either direction away from A, and that it's consistent for all power series, that they have one that works for them. Anyway, so that was a theorem. And then some of the properties that were discussed is that you can add power series together, but more importantly, you can differentiate them, you can integrate them to get new power series, you can multiply them by a power, you can even make a composition by plugging in a higher power of x. So there was a theorem about that. It gave us tools for manipulating power series and thinking about them. And so we will spend whatever time we have left looking at a couple examples of that. In any event, so in 9.2, they basically, in general, talked about some power series and how you can think about an infinite degree polynomial as an alternate way to express the value of a function. And the geometric series was our initial example of that. So then in 9.3, we combined these two together. We went back to the idea of a Taylor polynomial, and then we allowed the degree, the nth order of the Taylor polynomial to go to infinity, and then we had an infinite degree Taylor polynomial, which is therefore obviously then a power series, which is an infinite degree polynomial, and that gave us a Taylor series. So a Taylor series for a function is a specific power series in which the choice of the coefficients of the polynomial is based on the formula that we used when we were creating the nth order power series. And so there was a definition of that. So let me put that here and remind us of that. So that was on page 685. So the power series is the series you get for the Taylor version, which is where you take the kth derivative of the function and evaluate it at the point of tangency or the center value of a, and you divide that by k factorial. And that little formula tells you how you get all of these coefficients, which you then multiply by x minus a to the k. So what this does is, specifically the coefficients in general of a power series are produced using this formula. And when you use this formula involving the derivatives of the original function and factorials in a denominator, then you get coefficients of a polynomial that gives the best possible approximation of the original function. As k goes to infinity, it actually agrees with the function, but only where the series converges, only where the Taylor series converges. And we looked at specific examples of that, figured out what they were. So as we created Taylor series for various functions, we saw that for many functions, you can express the value of the function as the result of an infinite degree polynomial, at least within the radius of convergence. And that gives us a way, and specifically, to think of transcendental functions as infinite degree polynomials that can be added, subtracted, differentiated, things like that. So there were some few examples we looked at, and then the examples were tabulated in another big important table. So let's refer back to that, and then we'll spend our remaining time doing a few examples. So the table was on page 694. So this led to, let's do this. Table of power series, Taylor series, basically basic results. 9.5 on page 694. Lists power series versions or power series of functions. So this basically is what they're building to. And then in 9.4, just to put it up here and we'll look at examples. After doing all this work to introduce all these concepts, they just simply do working with Taylor series. There's no new information in 9.4, but they spend time basically with the series in that table, in table 9.5, and using those with differentiation and integration and multiplying by things and plugging in to get new series for related functions that are like the ones in the table. Okay, so I'm going to look at the exercises at the end of the entire of chapter 9, since we only have about 10 minutes left. So there are review exercises for chapter 9, and then maybe we'll just try to see if we can pull up a couple of those. So these are on page 705. So let's see if we get through a couple of batches here. So looking at the first batch, it says find the nth order Taylor polynomial for the following functions centered at the given point. And so let's look at 4. It has f of x equals e to the minus x. It says that n equals 2. So that means that's the nth order is the second degree, and a is 0. We did an example very, very similar to this. And also just a vocabulary reminder, when a is equal to 0, that's called the Maclaurin series. Okay, sorry about that. So we want basically a quadratic, a second degree approximation of this function, second order Taylor polynomial. So to calculate that, we need to know the derivatives. So in this case, just for notation, we want the summation. As k goes from 0 to 2 of the kth derivative of the function, evaluated at the center 0 over k factorial times x minus the 0 center value to the k. So the big thing in the formula that we need to figure out to do these coefficients is the nth order derivatives. So f, the 0th derivative of the function, is the function. So that's e to the minus x. The first derivative of the function. If I take the derivative of e to the minus x, by the chain rule, a minus 1 pops out, and I get minus e to the minus x. I take the second derivative, I take the derivative again, another minus pops out, getting me back to e to the minus x. And then we have to evaluate these as 0 and plug them in to get the coefficients. So when k is equal to 0, then I would get e to the minus 0 over 0 factorial times x to the 0. And so that's all just a big fat 1. When k is equal to 1, I would get minus e to the minus 0 over 1 factorial times x minus 0 to the 1. So that's all a negative 1 out in the front of an x. So I would get minus x. And then finally, when k is equal to 2, looking at the second derivative, it's back to e to the minus x. I would get e to the minus 0 over 2 factorial times x minus 0 to the second power. So that's a 1 over a 2. So that would be 1/2 x squared. So my resulting second order Taylor poly for e to the minus x at a equals 0 is 1/2 x squared. There's the highest degree term, minus x plus 1. And they may actually write that in ascending order, because since we got the first one first, the second one the next. But if you look at it as a polynomial, it looks like that. So that's example 4. and a quick review just of the mechanics of coming up with the coefficients for an nth order Taylor polynomial. So let's look ahead in the exercises. Probably time to just consider one more. All right, so how about looking at number 27? So it says, use the geometric series to determine the Maclaurin series and the interval of convergence for the following functions. And for this one, they give us that f of x is equal to 1 over 1 minus 5x. Sorry, plus. Okay, so the thing to point out about this is that this is a function, and we're trying to look at the idea of writing a series or a power series for this function. And so what I would point out is that on the table, 9.5, where you're going to want to spend quite a bit of time so you get used to what's there, they have that 1 over 1 plus x is a modified version of the geometric series. So you have 1 minus x plus x squared, etc. And that this is valid whenever absolute value of x is less than 1. This is like number 2 on the thing, less than 1. They just basically took the formula for the geometric series and swapped the minus x with a positive x. So what we want to do is we want to use this, but now instead of an x, we have a 5x. So that means every place that this had an x, we would swap it out with a 5x and put those into each of those positions to get our new series. So this table is really, really handy to do a lot of problems. So in this case, that would give us that 1 over 1 plus 5x is equal to 1 minus 5x instead of x, plus 5x squared minus 5x cubed, etc. And you could apply the powers to some of those 5s to get those coefficients, and that this is going to be true whenever the absolute value of 5x is less than 1, which instead translates into the absolute value of x being less than 1/5. So that gives us our radius of convergence is 1/5 instead of 1, and it gives us our new power series.